So earlier this year, a blurry picture was on the cover of newspapers around the world. You may have seen this picture. It was the first image ever taken of a black hole. This image swept the world. It's estimated that billions of people saw this ring of light surrounding a supermassive black hole. And scientifically, with this image, we had achieved a huge milestone. We had shown that it is possible to take the direct image of a black hole and use it to probe our understanding of gravity. Humanity had taken a picture of something that seemed impossible, and that really captured people's imaginations. But as inspiring as I find this photo to be, I find this photo of the group of us that made it possible just as inspiring. The black hole image was the result of 200 astronomers, physicists, mathematicians, and engineers from around the world who worked together to achieve something that wasn't possible for any one person to do. To do this, we brought together people from North and South America, Asia, Africa, and all across Europe. In fact, this photo was taken here in the Netherlands in Nijmegen just under a year ago at our collaboration meeting. So today I want to tell you a little bit. So today I want to tell you a little bit about how we were able to work together to take the very first picture of a black hole. So black holes are one of the most mysterious objects in the universe. They're cloaked by an event horizon where extreme gravity prevents light from escaping them. Yet the matter that falls onto a black hole is actually superheated to hundreds of billions of degrees, so that before it passes through this boundary, it actually shines very brightly. And for that reason, although black holes are relatively small, they can actually outshine the combined starlight of all the stars in their host galaxies. And so scientists have been studying black holes ever since they were first predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying the giant elliptical galaxy at the head of the Virgo constellation. This galaxy, called M87, is 55 million light years away from us. Many years ago, someone discovered a streak of light on the sky, which is a galactic-scale jet of plasma that was shooting out of the center of this galaxy and marking the spot of a supermassive black hole. And so ever since then, for decades, scientists have been building better and better instruments to study this jet and the black hole at its center. And in 2017, an Earth-sized telescope hooked up together and took the data necessary to see the black hole at its core. And after 2 years of processing the data, this is what we saw. But you might ask, how are we able to take a picture of something that by definition should be unseen? It doesn't let light escape. Well, light propagating near a black hole doesn't actually follow straight lines. Because the space-time is curved, actually photons move in curves. So photons can even go in complete circles around the black hole. And so, as I said, you have this gas around the black hole. It's superheated, so you have these photons flying around everywhere. And some of these photons fall into the black hole, but other ones just graze it, and they're curved around, so that the net effect is that the black hole casts a shadow on a backdrop of this hot material, making a ring that's almost perfectly circular. And if Einstein was right about gravity, then the size and the shape of this ring would tell us about the mass and the spin of the black hole. And this is often referred to as the black hole shadow. So simulations of the turbulent plasma around a black hole, computer scientists and theorists predict that we would see something like this if we could see at around a 1 millimeter wavelength with infinite resolution glasses, basically. But even if it is possible to see the direct environment around a black hole, taking this picture is really hard for a number of reasons, but one of the biggest ones is that this ring is incredibly small. So it's 40 microarcseconds in size, which is about the same size as a grain of sand, but when that sand is in New York, and we're viewing it from the headquarters of Databricks in San Francisco. So it's really, really tough to take a picture that small. And the reason why is it all comes down to diffraction. Diffraction tells us basically the smallest objects we can see. And so by plugging in the necessary wavelength of light and the angular resolution into the diffraction limit equation, you can easily calculate that we'd need to build a telescope that was 13 million meters across to see this black hole. And if we could build this Earth-sized telescope, we could just start to make out the distinctive ring of light that's indicative of the black hole's event horizon. Well, obviously, it wasn't possible to build a telescope the size of the Earth. But by joining telescopes from around the world, the Event Horizon Telescope collaboration built a computational telescope that's the size of the Earth that is capable of resolving structure on the scale of a black hole's event horizon for the very first time. So how does this work? Well, to understand it, let's go back to the basics of just how a regular radio telescope works. Okay, so radio telescopes act essentially just like giant mirrors. And so light from the black hole is going to travel to Earth, and it's going to reflect off of a parabolic mirror, this dish, and combine together at the focal point. And so the whole reason that we can get this, this really fine resolution is because we're combining light from a large area. Okay, well now imagine that we didn't build this Earth-sized telescope, but we instead laid mirrors all across the Earth, and we collected light, essentially turning the Earth into a giant spinning disco ball. And then we collect the light at each one of these tiny little mirrors, recording the data we collect at each one of them, and then we combine it in a computer. Well, if we did this, we would get a picture just as good as the one that we had with the giant Earth-sized dish. But now let's imagine that we removed most of these mirrors, so only a couple of them remain. Well, that's exactly what the Event Horizon Telescope has to deal with. In the Event Horizon Telescope, we have a number of disjoint telescopes located around the world that were actually built for completely different purposes. But by putting specialized equipment in each one of them, including atomic clocks, we're able to essentially freeze the light at each of these locations, and then we record petabytes of data, and we bring that data together and use our computers to act like the lens to make the final picture. So there are many parts of this project, from the instrumentation to the theory, calibration, tons of areas that need to work to make this computational telescope work. My primary role in the project was working on the techniques and the algorithms that allow us to take this data and make an image from it. So how do we do that? Well, unlike with a regular camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead in frequency space. So we essentially take measurements of the black hole image's Fourier transform. And if we covered the Earth in telescopes, if we tiled it in telescopes, we would capture all these spatial frequency measurements. But because we only have telescopes at a few locations, that means we only see a small number of them. And so it turns out that for every 2 telescopes in our telescope array, we actually get a single measurement of the underlying image's spatial frequency that's related to the projected baseline between the telescopes. Okay, but in 2017, we observed with 8 telescopes, but actually of those 8, only 5 of them were actually able to see the black hole in M87 and were at different locations. So that would be only 5 choose 2, only 10 points that we'd have to try to use to make an image from. But luckily, as the Earth is rotating, and one point I want to highlight is each of these points actually has both an amplitude and a phase. Okay? This will come in hand. You should know this for later, I guess. So as the Earth is rotating, we actually obtain other new measurements. So since the baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane. So what do these points mean? Okay, well, when you have telescopes that are close together, that means you're going to get short baselines, and that corresponds to low spatial frequencies, so that tells you about broad structure in the image. And so to get the fine detail we need to see the ring, we actually have to put our telescopes as far apart as possible. So if you're not that familiar with what a Fourier transform is, I like to think of each of these measurements a little bit like notes in a song. So each of the measurements we make corresponds to the tone of one note in a piano, and the measurement at a different location corresponds to a different tone. And so watching the black hole with the Event Horizon Telescope is a little bit like listening to a song being played on a piano that has a lot of broken keys. Even if there are a number of them that are broken, as long as you have enough functioning keys, a lot of times you can still make out what the underlying song is. And so at this point, we can kind of abstract away the astrophysics of the problem and think of it as just a mathematical problem. We have this sparse data, and our goal is to find the image that caused it. And again, if we covered the Earth in telescopes and we captured all these spatial frequency measurements, it would be trivial. We could just take the inverse Fourier transform of the measurements to make a picture. But because we have only a few samples, that means that there are an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, the fact that there's a different, quickly changing atmosphere above each of the telescopes makes the data incredibly noisy. And I want to try to emphasize these challenges of the data just so you understand how this kind of works into the way that we make images. So the whole key to how we get data from the Event Horizon Telescope is the fact that light from the black hole, it's going to travel to Earth, so it's going to take 55 million years, and then when it reaches Earth, it's actually going to reach one of the telescopes slightly before the other one. And that time delay is key for extracting that 2D spatial frequency measurement that we use for image reconstruction. But when you have a different telescope in Hawaii, then one in Chile, then one in Spain, they actually have different atmospheres above them. And those atmospheres cause a different propagation delay. So it takes the light a different amount of time to reach each of the telescopes. And that corrupts our measurement by adding a random phase into it. And similarly, this atmosphere also causes a different attenuation factor, also changing the absolute amplitude. So this error is very challenging because ideally we would measure this nice Fourier component, the italicized V that has both an amplitude and a phase. But in reality, we actually have this totally random phase error and a pretty bad amplitude error as well. So that's pretty terrible because at first glance, we've lost both our amplitude and our phase. And so, what do you really have left at that point? But if you notice, every measurement we make is from the combination of data at 2 telescopes, and these corrupting terms are station-based. They're from each telescope. And so if we replace telescope 1 with telescope 3, notice that the measurement actually contains some of the same corrupting terms, G2 and Phi2. And so we design algorithms to take advantage of this redundant corruption when solving for our images. And to do this, we developed 2 classes of imaging algorithms to tackle the problem. The first class of algorithms is based on a very standard method used within radio interferometry called CLEAN, but it's paired with something called an iterative self-calibration loop. And this is a more traditional method used within the astronomy community, and for that reason, it's very well vetted and understood within the community, but it was actually developed to be working on telescope arrays that work at much longer wavelengths and that have more telescopes in them. And so for the Event Horizon Telescope data, it's pretty difficult, and so you often need a lot of guidance from a knowledgeable user to move it in a direction that gets reasonable results. On the other side, we've also been working more with new algorithms, developing what we call forward modeling methods that don't just try to make an inverse function that takes us directly from the data to an image, but instead says, okay, I want to try to find an image that when I pass it through the forward model of what the telescope system is doing, I get data that matches the data that I take, the measurements that I've taken, but also is reasonable under some sort of defined mathematical prior or regularizer that basically scores how good each image is. Okay, and the disadvantage with these methods is that we have to define what is a reasonable image, and that is always going to add bias into our problem. But the huge advantage of these methods is that we can naturally incorporate all the different kinds of errors that we expect to see on the Event Horizon Telescope data and take account of all that atmospheric air that I talked about earlier. Okay, but both of these methods, all methods that we'd ever developed to handle this problem, have to inject some sort of information into the problem about what images look like in order to get something back in the end. And that will bias our final picture. And so, for instance, we wouldn't want to assume, accidentally even, that our image should look like something like a ring, and then be really excited that we got a ring back in the end. So we had to be really careful when reconstructing our images. And so the big question we faced in dealing with the black hole M87 data was not just how do we make an image, but actually how do we verify what we're reconstructing with our imaging algorithms is real? And we tackled this through a multi-step process. The first step actually began years before we even collected data, and that was to run synthetic data tests. So we did this through what we called the Event Horizon Telescope Imaging Challenges, where we'd have a team of people who would generate synthetic data sets as if the Event Horizon Telescope were seeing some source in the sky, and they added all the different kinds of crazy noise that we expected into the measurements. And then they would make these data sets publicly available, but without telling anything about what the underlying image that they used was. And then groups of people would use the methods that they developed and independently reconstruct, make their best guess at what they thought the underlying image looked like. After this was done, the images then were passed off to a team of experts who would look at the images and try to assess, what do I believe in these images? What don't I believe in these images? And this was really similar to what we'd have to do with the actual data. But unlike with the real black hole data, we knew what the true image looked like, so we could compare it to it in the end. So I just want to show you a few examples of things we saw in these challenges and how we use this to approach the actual data. Okay, so here's one example of one of the challenges. On the top is the truth image that was not given to the teams while they were doing the reconstructions. And on the bottom, it shows 5 different methods that were reconstructed with different people reconstructed them independently. And one thing you might notice is that each image actually looks slightly different. However, there are similarities across them. All of them kind of have this crescent shape that's brighter on the left than the right, but the wispy structures that come off of them is very different. And so by comparing what we see in common across these images and what's different, we can gain or lose confidence in certain features. Another thing we did, though, is also we threw crazy things into the challenges that no one was expecting. So for example, this was one of the challenges we put in. And obviously, no one was expecting there to be a snowman in the center of the galaxy, and the methods definitely weren't expecting something like this. But despite that, we were still able to get this surprising structure. And so that gave us confidence that we would be able to get something surprising in our real data, and we weren't just searching for something that we wanted to see. So based upon these synthetic data tests, we approached how we were going to go about handling the actual M87 black hole data. So we wanted to avoid shared human bias like we had done in these imaging challenges in order to assess the features among independent reconstructions. And so to do this, we split about 40 people who either develop imaging methods or who are very good at using these methods, have a lot of experience in them, into 4 teams that span the Earth. And these teams actually, during the initial imaging process, were not able to talk to each other at all. And so we were given the data in June of last year, and then we were told to work in isolation to try to make our best images from the data. And so, for instance, I was on team 1. We got our data, and we ran into a little room, closed the door, and we all had our imaging scripts available, ready to go, and we pressed go at the same time and watched as the images appeared. And it was a very surreal experience, actually. It was a lot of fun. But this is the image that we created after about an hour or 2, I think, on the first day of getting the data. And it was a thrilling experience, but we still weren't sure. We weren't sure how much we were biasing in a certain direction. And so we spent the next 7 weeks trying to make sure we believed this image, perfecting it, understanding the data problems, and exactly what we thought the uncertainty in that image is. And after 7 weeks, we all gathered together in Cambridge, Massachusetts, and we revealed the images to one another. And this is what we saw. So it was really amazing. Although each picture was different, just like in those imaging challenges, they all reconstructed the same basic structure. A ring of roughly 40 micro-arcseconds that was brighter on the bottom than the top. And so seeing these images was one of the happiest moments that I've had in the collaboration. And that's because despite having reconstructed images myself before, it wasn't until I saw that different people using different methods all recovered the same similar structure, underlying structure, that I really believed that had a lot of confidence in these results. And so I think it was really important, this aspect of the problem. But we still wanted to make sure that we weren't biasing it too much in one direction. There was still human bias in these results, and we could have all been pushing it towards this ring shape. So we spent the next couple of months essentially trying to break these images. And that led to the 3rd step, where we tried to objectively learn different imaging parameters to remove humans from the loop as much as possible. And so to do this, we developed 3 different imaging pipelines. You can actually download these pipelines, the scripts, everything, the data online on the Event Horizon Telescope website. But each of these pipelines, like lots of methods, has its own individual knobs on them that are usually tuned by human users. But instead of having a human tune them, we instead wanted to search for the best set of knobs to recover different kinds of source structures. So for instance, we generated synthetic data as if the Event Horizon Telescope were seeing a disk on the sky with no hole in the center. And then we ran our methods and tuned the knobs to best recover that disk shape. And once we had found those parameters, we then transferred it onto the actual M87 data. And although we had tried our hardest to make it find a disk with no hole, the data required us basically to put a hole in the center. And by doing this simple training and testing procedure on many different types of underlying sources, we saw that our methods always preferred this ring shape. And that was true no matter the day we observed M87 on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed the rest of the world on April 10th, an image that we really believed, this ring of light that was brighter on the bottom than the top. But once we had made these images, we still weren't sure. So we went through a number of validation tests. I'm going to just highlight one of them here. So previously, I talked about how we selected this set of parameters, how we tuned these knobs to best recover different kinds of source structures. But why should one set of knobs be the optimal set? In fact, there's usually a lot of knobs that recover reasonable structures. And so instead, we set some threshold, and we said, OK, let's just find all the parameter settings that recover reasonable structure for this synthetic data and apply it onto the M87 data and see what kind of variations we get out in the end. And so, for example, for one of the pipelines, we ran hundreds of thousands of different simulations, and we chose roughly 1,500 parameters that we thought were acceptable. And so, for example, here is a slice of 2 of the parameters that we searched over. The green boxes are showing the parameter settings that we had selected as being reasonable based upon tests on synthetic data. And once we had gotten all these different reasonable reconstructions, about 1,500 of them for the one pipeline, we could then look across them for variations. So on the left, it's showing the average image we found by aligning these images, and the middle is showing the standard deviation of them. And so you can see along the ring, there are areas where we have less confidence, and that is related to the underlying point spread function of the telescope array and the source structure. However, the uncertainty we have, those variations along the ring, are much less than the flux of that ring. And so if you look at the fractional standard deviation, you see we have a lot of confidence in that ring structure. It appears in basically every image that we reconstruct, but all that wispy stuff outside of it, we have basically no confidence in, so just don't believe that part. So, once we had made these images, the whole reason that we're making these images is to do science, right? So the question you might have at this point is, what did we learn? Did we prove, for instance, Einstein was right? And the short answer is, no, we didn't prove he was right, but we also didn't prove he was wrong, which is also big, because we showed that we were consistent with gravity at a whole new level. And so I just want to give you an idea of how we can use this image to learn something about gravity, learn about black holes. Just one example. So if you take some fixed size mass, you can actually calculate the radius you need to compress it down into in order to form a black hole. In the case of a non-spinning black hole, this would be called the Schwarzschild radius. That would be the event horizon of the black hole. But actually, we don't expect to see the event horizon. What we expect to see is called the photon orbit, the point at which photons are orbiting around the black hole. And that's going to be a little bit bigger than the event horizon. But actually, as the photons fly off of this photon orbit towards us on Earth, they're lensed out a bit. So we don't even see just this photon orbit diameter, but actually it lensed out to about 5.2 times the Schwarzschild radius, or 5.2 times the event horizon in the case of a non-spinning black hole. And if you have a maximally spinning black hole, it gets pulled in a little bit, so about 4.8 times that Schwarzschild radius. And so this is the range of diameters between 4.8 and 5.2 times the Schwarzschild radius that is the range for canonical general relativity for black holes. But notice that this ring size is depending upon the mass of the black hole. And that's really interesting because actually before the Event Horizon Telescope images came out, there were drastically different estimates of what the mass was. Gas dynamics thought it was about 3.5 billion solar masses, and stellar dynamics thought about 6.5 billion. And so stellar dynamics provided an upper limit, as there couldn't be more mass within the stellar orbits than just from the black hole. So we wouldn't expect the ring to be any bigger than that yellow one. But then we can say, OK, how do we turn this into a test of black holes? Well, we could ask ourselves, how about some other exotic objects? For instance, wormholes also produce shadows, but for the same size mass, they're actually a much smaller shadow size. And also, naked singularities, or super spinning black holes, also produce shadows, but they're even smaller. And so when you lay the Event Horizon Telescope on top of them all, you instantly rule out all these other exotic possibilities, and you're left with a ring size that is the same as the stellar dynamic measurement. And so this is just one of the many things that we can learn about black holes and gravity by studying this image. But perhaps the most amazing we saw is that by comparing this picture to simulations scientists have made for years about black holes, we find that the image taken is actually amazingly consistent with a number of these predictions. But you actually might notice that this simulation is moving. So do we see similar evolution in our own images? Well, it turns out that we actually we measured the black hole on 4 different nights, and we independently reconstructed images from all of them. And if you stitch these images together to form a movie, you actually see a little bit of evolution. So I'll try to play it for you here. It's a little hard to see, so I'll play it again. Notice this time the brightness is kind of moving more from the left to the right. So we don't actually have a good idea of exactly what is causing this variation. Is it rotation, or it's just material that's lighting up and getting dimmer? But what we are really sure of is that the time variability does exist. And that's because we see it in the raw measurements. It's very clear in the data. Statistically significant evolution is there, and we know that something has changed. And actually getting a hold on this time variability is quite important, because the space-time around a black hole, as described by the no-hair theorem, is actually fully defined by only its mass, its spin or angular momentum, and its charge. In effect, there are no other hairs on a black hole that we need to take into account when we're seeing how it affects its environment. And so astrophysical black holes aren't expected to have any charge, so really only the mass and the spin matter. But the mass is making the biggest effect on the ring size, and the spin is only causing an effect of about plus or minus 4%. So just using a static image to get a handle on the spin is hard. So observing an evolving black hole can help us in our quest of confirming or rejecting general relativity, because it gives us another way of measuring the spin. And so although M87 is wonderful, because it is such a big black hole, it's actually about the size of our solar system. And so it takes about 4 to 30 days, depending on the spin of the black hole, for gas to make a full orbit around it. But actually, there's a supermassive black hole in the center of our own Milky Way galaxy called Sagittarius A star, or Sag star for short. And it's a much smaller black hole. So it's only, in comparison to M87, a measly 4 million solar masses. And that means over the course of a night of observing, we see a huge amount of evolution in the black hole, because the gas is making a full rotation every 4 to 30 minutes. And so that means over the course of a night, we're seeing not just basically a snapshot, but a movie of a black hole. And so for this reason, we've been developing methods that allow us to propagate information over time, and in order for us to be able to recover not just a still image, but a video of this evolution. And so using these methods, we've been able to make progress in understanding how we can recover videos from evolving data. However, simulations of reconstructions of Sag star with the array that we observed with in 2017 show that we just don't have enough measurement coverage in order to make really clear videos of the black hole. So although you may be able to see roughly the ring size, we can't see that gas that's spinning around it that we need to recover the spin very confidently. And so for the future, we're considering adding space dishes to the array so that we can carve out huge swaths of the spatial frequency space very fast. And so by putting a low Earth orbiter into space, we might be able to quickly rotate around the Earth in order to capture many more measurements. And to explain how this can help, I just want to show that measurement space again and how we carve out those measurements. So remember, as the Earth is rotating, we get these different frequency measurements. But when we add just one orbiter to the array, look how much faster it carves out for that frequency space. And so we would have much better sampling over short periods of time, and hopefully be able to use this to reconstruct videos over a night. And by just adding a couple more orbiters, you can see that the space fills up incredibly fast. So this would be amazing in capturing much more detail about the evolution of black holes. And so with this improved array, we hope that we may be able to, in the future, not just make still images of black holes, but actually videos of black holes as they're breathing and evolving over the course of a night. And being able to track the dynamics, we might be able to learn even more. And so by linking up computational theorists who make predictions of what black holes look like, with instrumentalists who think of new ways to improve our Earth-sized telescope, and merging this information using computational imaging, feature extraction, algorithms, we've been able to start making progress on studying these really challenging sources. And hopefully we'll be able to show you a video soon of a black hole rather than just a static image. And so really, we're just at the beginning. Now that we have this extreme laboratory of gravity, we can go back, ask the questions, improve the algorithms and instruments in order to tackle these questions and learn even more. But I just want to mention again that none of this work would have been possible without the amazing set of interdisciplinary collaborators that I have the opportunity to work with. I'm so lucky to have this opportunity to work with this talented group of scientists who really pushes the boundaries every day. And so I hope going forward, you have the chance to work with some amazing researchers, go in unexpected directions, and do something that others also think is impossible. So thank you.